Okay, good morning, everybody. Let's come back to this second talk of today's morning session. And this should be given by Dr. Tokuro Shimokawa. And he's going to tell us about excite diagnostic method. So there will be two talks followed by a tutorial session. Right? So this is what the plan is, so that you get an idea about this method and also learn how to use it. Well, so over to you.
Yeah. Good morning, everyone. And here. And yeah, first of all, I'd like to thank the organizer for organizing this nice workshop and also for giving me this chance to here. I'm very happy. And then I'd like to talk about the details of the exact diagnostic, especially for the compensation system. And but before going to the details, so let me have time a little bit about me, because you have a question about who you are. I think that is natural. So we are here at Elementary, and I'm from Japan here. And actually, I was born in the mainland of Japan, but this time I'm from this small island in Japan, Okinawa Prefecture. And I think it's hard to see you. So there's a magnified view of the small island, and I'm from this small village on. But yeah, this island is very beautiful, and this is my institute, and Okinawa Institute of Science and Technology, and this is in front of the beautiful ocean. So this is our group photo of the theory of quantum number units, and okay, oh sorry. So this is the head of our units, Professor Nick Shannon. I'm here, and our institute and the units are international. So actually, we have many students from abroad, and yeah, two PhD students are from India, and one also is from India. So I'm very happy to visit their country, in the end. Okay, so I'm working as a staff scientist in this unit, and my field has been the physics of the confined classroom process system. So actually, so I have recently investigated about the high field of physics in SQL Park and arbitrary airstream of the system by using exact implementation methods. And I have investigated the mass focus in the cross-canonical of the system by means of the cross-canonical techniques. And I have experience to use the finite temperature lambda spike methods for the SQL Park thermal model. And I have developed with my collaborators new ED method to specialize high field. And which were applied to the content study in the value breaching problem system, and also for the content kinematic state in the spheroids macro. And that's all. So I have a few experiences to use the exact methods. So that's why I'm here. Okay. So I was asked to give the EV tutorial from scratch, or I assume that everyone is not familiar with the EV method itself. So in this tutorial, and I set goals. So I'd like you to understand the principle of the lambda space EV method in this tutorial. So actually, so the detail will be given about the Langeos and the finite temperature Langeos and the continuous fraction method. And these are the fundamental techniques to investigate the quantum state property or finite temperature and the dynamical features of the quantum matrix by using the ED methods. And I will focus on the SQL Hub system. One reason is for the simplicity. And the other reason I thought that I think it is good to know about the bit representation and the bit expression, and for making the efficient and the fast SQL Hub VD4. So actually, I will give some details about the two goals. And but I think that's kind of the stuff that could be the passive as learning for you, because of course, I think just listening to what I say is also the learning. But for your better understanding, I also prepared, I think, ED sample codes written by Python to be, I think, easier for the person who are not familiar with the computational language. And the lecture notes and the Python codes are available from this link. And that's I don't think you can access via the Wi-Fi network from this one. I don't know. Yeah, I hope you can. But then so you can access this website later. When this website link was already on my Slack, so that please access to the workshop website for accessing and finding this web page. Okay. So, this is outline of my tutorials, and I would like to first the introduction about some kind of the basic situation and background. And as my first lecture, I will talk about the Lantis methods and the content fraction methods for the same dynamics, and I also talk about the final temperature methods. And in the second talk, I think that's the line. So I will talk about the binary representation and the visual operation. These are the very fundamental and essential techniques to make a partially code for the basic spin system. And I will also talk about the symmetries in the graph diagonalism techniques, so to reduce the computational cost. And I will explain the detail of the simplest graph diagonalism techniques with using the multiplication conservation. And in that case, we should make, I think, the lookup in the table, I think, between the basis states. So you will learn the details. Okay. So let's start the introduction. Okay. So I think that the diagonalism is very fundamental techniques, I think. And this is the numerical techniques used for Schrödinger equation of the quantum many-body system, as previous speakers talked a lot, I think. So if you can diagonalize the quantum many-bodies Hamiltonian, and if you can get all eigenvalues and eigenvector of the quantum Hamiltonian, you can calculate everything by using the eigenvalues and the eigenvectors based on the ensemble of any temperatures, of course. And you can also evaluate the spin dynamics or dynamical feature by using the Green function and with using the eigenvalues and eigenvectors. If we could do for any lattice sizes, that's very nice, but we cannot do, unfortunately. So, let's see the situation with the simplest model. I will show first the exact diagonalization. How should I exactly diagonalize this simplest model, a simple Heisenberg model, and the two-spin system? So I'm showing here that this circle has a lattice size, and spin half degrees of freedom are localized in each side. And this black bonds means the interaction between the spins. So now the Hamiltonian is described this equation Si dot Sj. So this is the side I and this is side j. They are connected by the black bond. That's in the interaction, extended interaction. And we can rewrite this equation by using the SG and S plus S minus now. So so this is a two-spin system. So we have the whole number of the spin bases, and up up and up down, and down up and down down. So this Hamiltonian can be described by using these spin bases, 4 bases, and we can get the Hamiltonian matrix as shown here. So I think you already done, I think, by yourself in some quantum mechanics tutorial or lecture, I think, before. And after the actual calculation, we can get this simple form of the matrix Hamiltonian, and it is easy to diagonalize, and we can get the eigenvalues and the eigenvectors. So there you can get the symmetric state of the ground state of this two-spin system, and we can get a perfect state, states as excited states for these two spin systems. That's easy to diagonalize. So that's for the n-spin training system, for example. That's quite difficult. Let me explain the detail. So now that we are dealing with the n-spin system, so the number of basis state is 2 to n, so they're exponentially larger and larger. So this is the matrix Hamiltonian, and the size of the Hamiltonian matrix is 2 to n, as I say. And we create a computational memory to store the every elements in this Hamiltonian matrix is here. So the 8 times 2 to n times 2 to n bytes. And so this is the assumptions we are using the double precision. That means that so for each number, we need to use the 8 bytes for the element. So this is a required computation memory. So in the familiar units, so for example, when we are dealing with the n equal 10 spin system, so that's just requires 8 megabytes. That is easy to run on your laptop. But for the n equal 16 size spin system, this requires 32 gigabytes. It's quite hard, I think, on your laptop. Maybe latest laptop can do. But n equal 20, 8 terabyte is required, so we need the help of the supercomputer and some kind of efficient techniques to reduce the computational cost. So the matrix dimension and the computational cost grow exponentially, unfortunately. So what we can do for the reducing the computational cost, so within the ED method. So to access the predicting or the finite size systems, for example, we can use the lambda type method for the T-code physics, and we can also use the finite temperature lambda type method for the finite temperature physics. And we can also use the continuous fraction method for calculating the evaluating the spin dynamics. And we can also use the block diagonalizing techniques by symmetry. So I will talk about some details about these topics, I think, from now. So let me explain first the Lange's method for the T-code physics. Let me explain that one. So I think the law of the quantum fluctuation is still less understood in quantum mechanics, especially the cyclic coordinate plastic system. I think have been mainframe ground for finding the interesting exotic quantum states, I think, such as the quantum spin linked states and the quantum spin nematic states. And exact diagonalization based on the Lange's method have been used to investigate the if the quantum state of the target system may have the semi-classical long-range order or not from the finite size system, such as with using Taylor state analysis. So let me show the Taylor state analysis a little bit in the next page. So I think the originally Anderson proposed this scenario. So the spontaneous symmetry breaking and semi-classical near order states can be revealed from the finite size spectrum. So this is a good example about this analysis. And we are now seeing about the S-equal-R scalar anti-harmonic Heisenberg model. And we know now the ground state can have a long-range order in the thermodynamic limits. But in the finite size system, we cannot see that the true breaking of the symmetry, continuous symmetry, unfortunately. So, but the finite size system may have, I think, the kind of the kinetic energy. So because the spin in the spin sector, the symmetry is not broken perfectly. So that's kind of the energy can be understood from the top, a kind of the top, I think, Anderson solve. So I think you may have learned before, I think, that from the classical mechanics lecture. So the energy of the top, I think, could be described by the squared angular momentum. So the now the angular momentum of the system is the spin angular momentum. So that means the total S. So the finite size system's energy can be described by the this equation. That means that it is proportional to the square total S. So what I like to say here is if we could get the narrow level state in the thermodynamic limits, so the lowest energy state of each spin sector could be on the straight line. That is a kind of a signature or smoking of the symmetry breaking in the thermodynamic limit. But we can get this signature from the finite size system. So actually, this is the ED Lantos calculation result. So you can see here lowest energy value at the each spin sector. So these data are on the straight line. And you can also see the size dependence of the straight line. So the slope is decreased with increasing system size. So in the thermodynamic limits, if they are quite degenerate state, that perfectly degenerate in the thermodynamic limits, then so we can see the true symmetry breaking in the thermodynamic limits. So that was the, I think, that's predicted, and that was processing exact diagonalization. So this is example of the Tau state analysis. And actually, this analysis worked well even for the SQL capturing about distance from magnets. And we now know about this magnets can have the 120 neural states in the thermodynamic limit. Actually, so that from GP methods, we can see the clear linearity in the lowest energy state of each spin sector. That's for the carbon system. That is the lowest energy states not on the straight line. So that it's kind of the signature. We don't have the negative level states. Instead of that, we may have the constantly later states in this carbon model. Okay. Anything interesting in the detail? I think that detail will be is given by this good textbooks and please access to this book.
Can I ask a question?
Yes.
Is there any easy way to understand why you have 1/n dependence in the H effective?
Are you talking about this one?
No. I'm talking the formula below.
Yeah.
H effective. You have a 1/n dependence, right?
Yeah.
So S is also linearly growing with n, right?
Yeah. Right. Yeah, I think I have one before. That's kind of the stuff. I forget. Sorry. Yeah. I think this factor depends on the system, I think. So, yeah. For example, if we got this in the natural state, in the thermodynamic limit, I think that's coefficient can be changed, I think, as far as I remember. Yeah, let me check later. So
Okay. Yeah. Thank you.
So, okay, and these computational results are obtained from the Lantis method. So that will talk about Lantis method from now. Okay. So before talking about the Lantis method, let me first explain the power method. So what is the power method? This is a simple method to get the eigenvalue of the matrix with the largest absolute value. In our case, I think our purpose is to look for the lowest energy state. So that is one of the largest absolute value states. So let's start from arbitrary random initial vector with 0. I wrote here, I like here. And this psi n means, and the en are the eigenvalues and the eigenvector of the d-dimensional matrix Hamiltonian. So that we can set the random interesting vector as shown here. So, and in this power method, we are multiplying the matrix iteratively until the resulting vector converges to the desired one. So that's in the ground states. So what we are doing in this method is here. So we are operating the k times the matrix Hamiltonian to the initial vector V0. And now we can expand this initial vector by using the eigenvectors of the Hamiltonian. So this Hamiltonian matrix is diagonal against this phi n, so that you can get the En and the K, En up to K. So we can factorizing out the En max. That means the absolute maximum, largest absolute value along the En. And in this balances, we can write this equation. And you can see here, here is now the En over En max. So the En max, as I said, this is the largest absolute value. So in the larger k value, then this one will be the 0. So and you can guess the lowest energy state. So this is the only survival vectors, and this is the corresponding the energy eigenvalues, energy eigenvalues for the ground state vector En max. But actually, so we can get the lowest energy state by using this method. But it's required large k, unfortunately. So Lancaster method is proposed to the one of the ways of the acceleration, the power method. So that was originally proposed by Lancaster in the almost 70 years ago, I think. That's too old, I think, but that's too efficient. So Lancaster method gives us the acceleration of the convergence over a simple power method by subtracting the component of previous vectors, Vk minus 1 and Vk minus 2, blah, blah, and from Vk. That means, so I think if you maybe you're familiar with the multiple method, I think we'd like to get the thermal equilibrium state respective of any initial Lamarck configuration. So I think for the acceleration, so we'd like to forget everything about the initial random vector we set as the first point. So and for that, so that we will subtract, I think, the information of the previous vectors. And in that case, so that's corresponding to the orthogonalization between each vectors. So let's see the details of the procedures in the Lancaster method here. So again, so I process the initial random vector V0, and this is now expanded by the ST basis, up, down, basis. So that we are now focusing on the basic of system. So the up, down was 0, 0, 1, 1 binary representation is a good, I think, to describe the spin basis. So Cn is a random coefficient, and the real or complex is dependent on the situation, but this initial vectors is normalized like this. So let's start the power method. So we are dealing with the one. We are dealing with this method as the Lancaster method. So I think it is the same to operate. I think the Hamiltonian. Now we are multiplying the Hamiltonian matrix to the initial random vector, but we are subtracting the information about the first initial spin vector. So that's alpha 0 is given by this equation. And also in that case, so V1 and V0 are also one of each other. So you can forget everything about the first random vector, initial random vector. So we are repeating, repeat again. So for getting the next vector V2, so we are operating the Hamiltonian to the V1 vector, and but we are subtracting information about the previous vectors. So to also normalize this V2 vector and V1 vector, so the alpha and 1 and beta 0 are written by this equation. So this V2 are also one out to the V1 and V0 at the same time. So, and we will do again and again so that we are getting the arbitrary k with k vector. And this, in general, the k vector is written by this equation. So, and alpha k minus 1 and alpha beta k minus 2 are written by this equation. So this vk are also one out to the previous every vector. So this is the details of the Lancaster method. So we are using these, I'm calling these vectors as the Lancaster vectors, and we are using these Lancaster vectors as a new basis to describe the matrix Hamiltonian. So what we would like to do is rewriting the original matrix Hamiltonian by using the normalized Lancaster vector Vk prime here. And that gives us the following that on our diagonal matrix D. So now the original matrix Hamiltonian is written by this, and this is the form of the three-diagonal matrix, and that is very easy to diagonalize by using some subroutines in the Java or in the Python subroutine, for example. And actually, the eigenvalues and eigenvectors of this three-diagonal matrix correspond to the eigenvalues and eigenvectors of the original Hamiltonian matrix. So, actually, in my Python example code, I use this Psyche link eigen three-diagonal, whatever I think. So I'm using this one to diagonalize this get three-diagonal matrix D. So it is easy to diagonalize. So we can get the eigenvalues and eigenvector from this trigonal matrix. So good thing is to know is the needed k value. I assume that's the m, large M. So this large M value for the convergence is just 100 to 1000. So the much smaller than the dimension of the original matrix Hamiltonian. So that is a good method, I think, to get the lowest and the first and the second excited energy states, for example. So, but we should be careful about the eigenvectors we can get from this diagonal matrix, 5L, because this 5L is now written by these quantum vectors. So we should rewrite these obtained eigenvectors in the basis of the original spin basis, SG basis. So now our eigenvectors we can get from diagonalizing three-diagonal matrix is written by this form. So this eigenvector is written by the normalized Lambda vector. So we should rewrite this eigenvector in the form of the original spin SG basis. So for example, to get Grom's wave function, that's correspond to the L equals 0 case. So phi L equals 0 vector. Now, and this DKL is actually the coefficient you can get from the diagonalizing three-diagonal matrix. And you can rewrite these eigenvectors in the basis of the SG spin basis. So this is the equation. Let's see the detail. And first, we got this eigenvector of the three-diagonal matrix, and thus this normalized Lambda vector should be written by this S3 form, S3 spin basis. So that doing this, and you can get the eigenvector of the ground state, and in the S3 spin basis. Okay. So this is actually my Python example code. And you can read I think later. And actually the Lantos coding is written by with using just 30 lines, I think. I'm not sorry, 60 lines, so not so long, I think. And I use I think the almost the same parameter names as far as possible. Yeah, so please access to my GitHub page later and release the contents of the simple Lantos consult.py forward later. Yes?
No question. So what is the essential difference between the power method and quantum? I understood that if I use the vectors generated along the power method and we diagonal, we orthogonalize these vectors and we make the effective, we may obtain the same result.
I think we can get same result, right? But I think that in the power method, we cannot forget to ask about the information the interrandom vector efficiently.
I think that just corresponds to orthogonalization.
Yeah, of course.
So the quantum method is, has a very efficient way to orthogonalize.
Yeah. Right. Yes.
Thank you very much.
Yes. Hey. So actually, I will I prepared, I think, example calculation for your hands-on tutorial. And as example, I use this basic of J1, J2 existing chain model. And one state phase diagram was reported in this Garrison's PRV paper. And this is the one state phase diagram. So now the small j means that it's over J1, and the delta means the element 30. And there are the three phases. I think this is a working just in like state, and this is the diamond state, and we got the spiral state here. And here's the famous Majunda Gaussian point. I think Majunda is very familiar in this co-alpha thing because he was.
He is the first director of this institute, founding director of this institute.
Oh,
Chanchal Majumdar.
I see. Yeah, it's thanks. Okay, and thank you very much. And so my example code, for example, can deal with the phase transition between the individual states and diamond states in, for example, there's like one case that is Heisenberg point. Yeah. Yeah, for example, this transition point can be evaluated by just the n equal 10 system, for example, graphing. So I computed the single gap and the single triplet gap as shown here for the n equal 10 spin system and the delta equal 1 system and delta 1, and by using my Python example code. And you can see that this crossing point corresponds to the phase transition point supported in this paper. So, so please reproduce, I think, later on the hands-on tutorial time. I think if you have any question, I think you can ask the lecture later. Okay. So, what is the advantage in this one? Yeah. Can you hear me?
Yes.
Yes. Okay. Okay, so let me explain about the advantage of this one, advantage of the Atlantis method. So the graph of this memory is significantly reduced from the diagonalization methods. So actually, this is the this is the required memory for the full diagonalization method, as I said before. So that requires the 8 times n bytes. So the huge memory we need. But in the Atlantis method, so this 2 to n is 10 to the 3 only, because we just have to 3 vectors at the same time in our computer. So the memory is reduced. And for example, for the 20 such clusters, I think we just see the 24 megabytes. But we cannot avoid exponential growth, I think, in the qubit space with including system time, unfortunately. I think now the largest system size is almost 50 size, I think. Of course, with using the supercomputers and the Prof diagonal techniques, very recently. And this advantage is in the Atlantis method. It's once vectors we get prime, they tend to lose also out here, unfortunately. So maybe to get the true excited state, for example, you may need to use the advanced Atlantis type method, such as the secret stuff method or LOPPCG method. So these are differences for these advanced methods. Okay. Yes.
Can I ask a question?
Yes.
So, is it possible to use the Lantos method for the all-to-all interrupting system?
Sorry?
All-to-all interruption. So, probably you assume that there is a short-range interruption.
Yeah, I think the matrix, if the matrix is processing,
Must be.
I
understood that the point is that you don't need to store the Hamiltonian itself in your computer. Right?
Yeah, I think computational cost just is proportional to the number of interaction form, I think.
And it is almost
Yeah, but
polynomial, right?
yeah, but I'm not sure how fast with the convergence. I think that's the long range interactive system. I think I have no experience to deal with this.
Thank you very much.
Okay. So next talk about size and the continuous fraction method. That is also important techniques to calculate the spin dynamics. So background, yes, spin dynamics is very useful concept, the magnetic order or disordered ground state and corresponding excitation in the quantum dynamics. So actually, the spin dynamics is accessible from some experimental techniques such as measurements, ESR, and NMR, for example. And this is a beautiful picture which was reported in this paper. And they deal with the famous one-dimensional quantum magnets, magnets, potassium kappa fluorine 3. So this is the experimental data of the inelastic Newton space measurement. We can see the clear Gordon-like behavior, continuum-like behavior that's corresponds to the spin of continuum, and that is clearly the match, I think, to the data answers. That is the exact result of the model. So we can get the exact spin dynamics features by using the data answers. So they corresponding to each other. That is nice results and surely an experiment. So so of course we can do something by numerics. So for example, the dynamic potential factor can be evaluated by using the Lambda-like procedure. So let me explain the details how to compute the spin dynamics by using the Lambda-like method. So first, we should think about the self-correlation function to get the spin dynamics. So now we are thinking about the situation where we already got the ground state wave function of 5,0 from the previous Lambda method. And then we can think about the time evolution of that ground state wave function. And we can get this self-correlation function by using this equation. So this is the operator A, and this is described by the Heisenberg representation, as shown here. So we should consider. We should consider to use all eigenstates of the D-dimensional matrix Hamiltonian, and if we got these eigenvectors, everything, so that we can write this equation here. So y equal the sum of the get phi n and the graph phi n state, I think. Yeah. And now the En is the corresponding the eigenvalues of these eigenstates of the original D-dimensional matrix. So so we can insert in this equation into the between the A data and A here. And now it's a Hamiltonian matrix is diagonal against this eigenstate of the phi n. So we can rewrite this equation with this equation. So you can get exponential En minus E0 times parentheses and t plus t prime and parentheses both the same time over h bar. So, and this is a time evolution of the quantum state wave function. So next is to think about the Fourier transform with respect to the t and the t prime. And that gives the real frequency correlation function C omega. So this is the previous function here. And we are dealing with the Fourier transform with respect to the t and the t prime. And now we can get this equation, this equation, that can be written by the delta function here. And we can organize this equation by using only one delta function, because this delta function can be dealt with the first. That's the actually, so these delta functions can survive only the case that's the omega prime h bar equal omega h bar equal En minus E0. Then we can get this equation here. So this is the C omega, that is the definition of the real frequency correlation. So to compute the spin dynamics, we should deal with this equation. So what's like, delta function is a little bit difficult to deal with, I think, in the computer. So we are thinking about how they write this omega delta function in the form of the Lorentzian function. So this delta function can be rewritten by using this Lorentzian function, by using the Lorentzian radius n here. And we can rewrite this equation to this by this equation. So, and substituting this delta function into the original shear omega function, and we can get this delta function back into the between the this here, and we can finally get this equation to evaluate the spin dynamics. So in the actual calculation, we should set the eta as a small value, such that theta equals 0.02 or something like that. And because we cannot deal with the n equal in the limit of n equals 0 limit in our computer. So actually, so the way is known to solve this equation. I think you are familiar with the mathematics. I think this is called by the resultant part. So that can be dealt with the continued fraction. So this equation can be rewritten by using the continued fraction method like this. And so that you can evaluate the spin dynamics by using this equation when we are using this A as the SDQ, for example. SDQ means the equal times spin structure factor. That means the Fourier transform of the local spin operator. So now, and there are the alpha and the beta coefficients. Actually, these coefficients can be evaluated from the moments of this equation. So that means that this alpha k and the beta k can be evaluated by the Manchester method again. So this alpha k and the beta k equal to the elements of the three-diagonal matrix obtained when we use this A and the phi 0 as the initial vector in the lattice procedure. So, for example, to get the Z component of the dynamic extension factor, so that we set A operator A as this is the Q, and that's the Fourier transform of the local spin operator, and Ri now is the position vector for site I. And in the actual calculation, as I say, that we set the small value in ether such as eta equals 0.2 or 0.5, for example.
Excuse me.
Yes.
What is Z capital Z in the second line?
Ah, sorry. This capital Z corresponds to this one, I think. Okay.
Omega H.
Omega H bar plus E0 plus I. Okay, sorry.
Thank you.
Okay. So this is actually my Python example code. And to compute the spin dynamics for the Z components, only I think less than the 50 lines are needed. And to deal with the continued fraction part, so that's made in this part. So just I think the 20 lines are needed to write the code in the Python. So you can see later the contents of this Python code later. So this is a calculation example for everyone. I think you can reproduce, I think, on the hands-on tutorial. And I use here the reciprocal half instrument Heisenberg chain. And for example, I'm focusing now that this Q equal pi point here. So that I'm plotting now the calculation result of the SQometer at the fixed point Q equal pi. And here's omega dependence of the SQometer. And I, for example, use the n equal 8, 12, 16, and 20 site clusters for the 1D Heisenberg chain by using my Python code. And for example, with increasing system size, you can see the sharp peak is shifted to the omega 0 region. That will be corresponding to the this point here in the thermodynamic limits. And with increased system size, you can see the several peaks in between the omega equals 0 and omega 1. That can be, I think, the continuum features in the larger system sizes. So you can produce by yourself later. So how many minutes I have?
Take you 15 minutes.
15 minutes?
15.
Oh, I
Not
see.
five, yeah.
Okay, next is about the final temperature lattice method. So I think the effect of the sum of fluctuations on the process system is very important. I think that from the viewpoint of the order values of the enhancer. And the numerical data of the sum value quantities are very important also for the experiments because the experiment will be done at the final temperature in general. So that's the compound process magnets are very less suitable for the QMC method, and the fluid diagonalization methods have severe limitation to accessible system sizes, unfortunately. So, and for this problem, I think complementary methods without the ensemble average here have been actually developed independently, such as the final temperature lattice method and transfer matrix on-carbon method, and transfer on-carbon method, Councillor, and the sum of composite method. Yes, and I will talk about the one of them, final temperature method from now. So, this method was originally proposed by Jubilee and Claire Lovis in the 1994. And let's see first from the fundamental stuff about the common ensemble. So, to estimate the thermal equilibrium states at final temperature by using the method, we should get the all eigenvectors and the corresponding eigenvalues of the Hamiltonian matrix H. So we should use this equation. So this is the Paxton function, and beta is the temperature, and A is the oscillator about the physical quantity. So this canonical expectation can be expressed by using the following equation. That means so with using the general with normal basis states, I will call this states as the n, and we can rewrite this equation by using this equation. So that is a linear algebra. So let's think about the expansion exponential minus beta h by using the vector. That means that corresponds to the high T expansion. So the form equation can be written by this equation in this form. So you can see here the multiplication with the matrix Hamiltonian to the A and the orbital vector M. So, and we should deal with and evaluate this term, I think, by using the Lorentz method. And so that means that we can set this n as the initial lambda vector in the usual Lorentz method. Then we can deal with and evaluate this term. So, for example, let's see the example. And first, I set this n as the V cell n. And this is the initial random vector, and that is written by the ST up down basis, for example. And this is normalized. And by using the Lorentz method, the iteration and the k equal m, which is larger than small l. So then we can set the Lorentz vectors again from the V0 n to the V k equal m n. And we can get the eigenvalues and eigenvectors, so we get diagonal matrix T n. And as I explained in the previous topics. So by using these eigenvalues and eigenvectors, and we can rewrite this term as this equation. So a little bit complicated, but this is just here's the first one here. Can you raise this? Oh. So just dealing with, for example, we define the projector operator. Oh, Um, um, yes. So this is a projector, and this projector can be inserted in the here, so the you can evaluate this equation. And you can insert this one here, 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 and this Hamiltonian is diagonal to this eigenvector by n. So you can get this equation in the end. So we can derive this equation, original these equations into these equations. So now let's see the summary in a sense. And so this blue line region corresponds to the Lantos part of each different initial lambda vector. So we should set the different initial lambda vector for each different n. But we can deal with by using Lantos method. And this is the this red line corresponds to the sum over the initial lambda vectors. But in this equation, this looks like that we should deal with the summation over d. That is amount, I think. So we can but approximate this summation by the summation over Q realization. I call this number is R, and that is much less than the D. D means the original Hamiltonian matrix, size of the original matrix Hamiltonian. And so that's this summation can be replaced by this summation. And plus we should see about the statistical error, like Monte-Carlo methods.
Excuse me.
Yes?
So could you explain a bit the second line of the
Second one, yeah?
so because Hamiltonian is diagonal is the basis of it. So is it approximation?
Or this, so we need to deal with I think summation over the large D here.
Okay, my question is the Hamiltonian is diagonal in the basis of phi.
Yeah.
And do you mean, sorry, I didn't understand the definition of phi. Phi is the eigenvector of the Hamiltonian.
Eigenvector of the diagonal matrix.
Okay, so it is the approximate.
I assume that I think that these vectors are corresponding to the quantitative function of the Lisman transform. For example, this is phi f by 0 n.
Yes.
Yeah, in a sense, approximation. Right? Yeah, in a sense, yeah, like it.
Thank you very much.
Yeah. Of course, to see the low temperature physics more precisely, I think you need to deal with the large m value, for example, because that large L m value is needed to get the true energy value, eigenvalues, I think. Yeah. Twice energy eigenvalues. So finally, we can get this following equation, and we can finally evaluate the expectation value that is the quantity A at the temperature vector by using these equations. And the scalar scales, it is known that the statistical error scales 1 over square root R R means the number of realization of the initial contesting vectors. And actually, so the high T regime, so that's the scala is very small because that scales 1 over square root RD. That means if the dimension size of the matrix Hamiltonian is large enough, so that only one realization is needed to get the true value. So, and for example, if the observable phase is commutable with some Hamiltonian, such as the energy, and it is very easy to calculate these expectation values. So, for example, the total energy and the specific heat written by this equation, and you can these equations. We can deal with this equation in my Python sample course later. And to deal with this curve, I think, so that corresponds to the zeroth component of the phi kr. Phi kr means the eigenvector of the two-diagonal matrix for the R. So that's easy to get this, as I'd like to say here. So after Python code written like this, and the left-hand side, we can see the part of the finite temperature lattice method, and that is written by just 30 or 40 lines. And these on the right-hand side, we can see the two parts in the for calculating the temperature dependence of the energy and the specific heat. So you can play with this code for getting the temperature dependence of energy and specific heat later. So that against example, for example, here, and that was the reported S equal Prof Heisenberg change specific heat that was obtained by the bed ansatz. And I actually run my Python finite temperature code by myself, and I treated the N equal 8 and the 10, 12, 14, 16, and I set the condition so the realization is 10 by 3, and n, that is a Lantz situation number. I just set a 50. So of the low temperature regime, you can see the deep final side effect plus with the system side. Yeah, that's kind of the bump behaviors will be decreased, and looks like the thermodynamic limit without the n. Okay. So okay, so the advantage of that finite temperature Lantz method, so the required memory is significantly reduced from that in the dynamic method, and almost the same as in the Lantz method. And that's the accuracy at low temperature a little bit worse, I think. So because to get, I think, the exact value, almost exact value at the extremely low temperature regime, so you need to use, I think, advanced finite temperature Lantz method, such as the replaced finite temperature Lantz method, which is the vote in this paper, for example. And of course, dynamical quantity, such as the SQ omega at finite temperature, also can be computed based on the finite temperature method. But I will not give the details, but if you're interested in the details given by this great group, so please read this group if you're interested. Okay, so that's all my thoughts like that.
Yes, thank you for a very nice talk, and you just finished on time, so I guess we have time for discussion. So questions from the students. Well, everybody's quiet. What happened? Tired after yesterday's?
Yeah, because of the bandwidth.
Yes, yes. So yes. So can you bring this thing?
Nice talk. So if we add speed, can we transfer speed? Hello.
Yes, okay.
The transfer
Yeah,
speed.
yeah. Other than taking this temperature, is that the same mechanism we can use?
Yeah, you can use it.
For the transfer field I'm talking about.
Yeah. And just to focus on this of Heisenberg system for the simplicity, but you can apply the finite temperature Lantz method if you are,
Thanks for the nice talk. In the slide 13, I saw
Slide number 30.
you mentioned
Number
the
30.
okay, I'll fix that.
30.
30.
So there was,
Oh,
yeah,
So
13 or 30? 1-3, right? 1-3.
1, 3.
The tendency of the
Wait a second. Exactly.
in the third configuration, the tendency doesn't seems like the matching the line you draw in the dotted line. This one.
A little bit louder.
In the triangular figure, the line you draw doesn't seem to like matching with the data in drawing. And you were, as I heard, you said like, this may be due to the emergent spin liquid. Is that right? Have I heard spin liquid phenomenon?
Spin liquid?
Yeah.
So are you talking about covenant?
Yeah.
Let's see.
So maybe I rephrase the question. So I think you argued for S equal to how triangular that is.
Yeah.
You have a 120-degree
Yeah.
ordered phase,
Yes.
and for this cargo wave, it doesn't order. So like it's been liquid.
Yes.
Right. So what is the
Could be.
argument? If you can
Yeah.
reveal the argument.
Yeah, but of course, to nature is under controversial is for the carbon system. We may have the VBC state, a balance one percent, maybe, I don't know. Spin liquid, yeah, press even spin liquid states. Yeah. But this type of set analysis, I think, indicated the kind of non-polar states in the quantum state sometimes limits because these lowest energy data not on the solid one.
So if I ask you, so what is plotted along the x direction is S into S plus 1.
This one?
No. For the triangular antichromatic lattice value, R equals to 150 order phase.
Yeah.
This is S into S plus 1 versus E by N. And if it crosses the straight line, then you have an ordered phase, right? This is what the argument is.
Sorry, understand your question.
So the question is that from exact diagonal addition,
Yes?
you can talk about spontaneous symmetry breaking.
Yes, from the final side.
So what is the argument for that? You can repeat that.
What is the argument? Okay, so I understand the question. So the spontaneous symmetry breaking can occur in the simultaneous limits only.
Yes.
So in the simultaneous limits, I think the symmetry of SU2 is broken down to the U1 symmetry. That can occur only in the simultaneous. So the final side system, so we still have the SU2 symmetry in same. So there is a kind of the motion of the spin system in the SU2 spin sector. So that's kind of the motion's energy is written and understood by the quantum top. Top, do you know the top?
Quantum top.
Top, yeah, top. Yeah. And as you may know, the energy of the top can be described by the which is proportional to the squared angular momentum. So in that case, angular momentum corresponds to the spin angular momentum. So that's really the total x. So,
Are there any questions? Yes, she has a question.
Hello. Thanks for the nice talk. So in the lattices algorithm, we have considered spin systems.
yes.
If you had to do the same for fermionic system, how would you incorporate the fermionic
What
statistics?
system is it?
Fermionic
Fermionic
system.
system, like the
Fermionic system.
Fermi-Hubbard model.
Yeah, Hubbard model.
How difficult or different it would be to
I think
incorporate the
statistical system size is very used. I think statistical system size is just small. I think. For example, Hubbard model, I think we can deal with up to the 20 side clusters. I think, for example.
yeah, but what about the fermionic statistics like exchange of particles, and you can now have double occupancy also.
Yeah.
And particles exchange will give you a minus sign.
Yeah.
How would you incorporate all that? Is it taken care in lattices algorithm, or you have to do something in addition?
Yeah, can be deal with I think, but I don't know that way because I have experience to deal with Hubbard model like these. Sorry.
So once you set up the Hamiltonian, right? So you can diagonalize better using Lang's-South method. I don't think there will be any problem in doing
So
that.
the problem is before.
Yeah.
The problem is you set up the Hamiltonian, which you can easily do. Right?
Yeah,
Once
for
you
the
set up a Hamiltonian,
Hamiltonian, you can apply
then
this.
you apply this thing.
Yeah.
Thank you.
Yes, the only restriction is how big a size you can do.
Yeah. That is a remaining problem, plus your big problem.
Any other question?
Can you ask from online?
Ask him to repeat it.
Shashikant Mohammed, please ask your
So
question.
thank you for the
Sir,
beautiful talk. So like I have few questions. So
Small
first
story.
is when we have to construct the web function in the original basis from the Lanchos web vectors. So this Lanchos web vector we get like exact answer only for the ground state or the few excited state. So how we can construct the original the web functions in the original basis?
Are you asking about the quiz part?
Yes.
Okay, yeah. I see. So, first, the left vectors are obtained by using this equation. So actually, so these left vectors are written by the ST basis. This is the original ST basis. So, but after diagonalizing this three-diagonal matrix, so of course we can get the eigenvectors for this three-diagonal matrix, but that is written by using the lambda vectors. So these lambda vectors are used as a basis. So these lambda vectors have the here is the n-dimensional vectors. So I think I should use the blackboard. I think. Um, yeah. So, yeah. Oops. Okay, so let me explain the situation for getting the eigenstate in the original ST basis. So after diagonalizing the diagonal matrix, we can get the eigenstate by L, example, E1, C2, C3, that is the coefficient. And now it's a I should start from 0, 1, 2, and C, and minus 1. Okay, so this is the n-dimensional vector. So to compute, for example, expectation value by using the quantitative function, we should rewrite this eigenstate in the basis of the ST basis. So that is, for example, this is a normalized Lanchos vector with prime, and this is the William line. Prime, and minus 1 prime. So what's we know already in this page. So this 3K vector is written by for example, E and E minus 1 and down basis. And this is n's basis. So right, if in this case is just substituting these Lanchos vectors into this here. So this VK prime is written by the ST basis. So just substituting this actual form of the VK prime into this. So you can get the coefficients of the quantitative function in the ST basis. That's kind of-
If we have to store that that SZ basis, it itself like the almost the same size. So is that any way of storing that basis like more efficiently so that it will take less storage? Because if you have to construct the whole bases, then it will take the same size. Like
Yes, right. So, yes, actually, so we should do the same Lantos procedure to get the ground state wave function, actually. So, but we cannot avoid this procedure. Am I correct to your question? Do you have another question or?
yeah, I have another one more question. So like I'm thinking of like so this we are taking that m less than the dimension like d to get the ground state. So suppose I am interested in finding the dynamics of system. For that we require the full set of eigenvectors or eigenvalues. Can we still employ the Lanchos method? Because though we have to create a large matrix, but still the matrix will be a very sparse form. So can we employ that Lanchos, and does it give the exact eigenvalues? If I take that m equal to d, does it give the exact all the eigenvalue same as the like the normal ED method?
Yeah. So I think you're asking about the how to compute the dynamics without getting the all eigenvalues and eigenvectors of the Hamiltonian.
So maybe I clarify. So what he says, when you do Langsdorff's method,
Yes.
you only get the ground state and few excited state,
Yeah.
the entire spectrum.
Yes.
But now if you want to map back to the original basis,
Yes.
how do you go about doing this? Particularly this will necessary when you calculate spin dynamics and so on. You like to say something?
Yeah, the point is that the
Can you ওটা ওখানে দাঁড়িয়ে থাকলে হবে?
Yeah.
দিন আমাকে দিন। আপনি ভেতরে বসে থাকুন। Give it to me. Send him inside.
See, the basis vectors are n vectors, which correspond to all the spin configurations of the n things.
Yeah.
Okay, and you only take linear combination of those form the Lanchos vectors. So you can actually go back and forth between the two things, because you have the Lanchos coefficients, and those coefficients are actually coefficients of the linear combination of the n vectors, which is the original vectors. So you can calculate all the properties using that. Okay.
I'm actually asking if I take that capital M equal to D, like if I apply D times exactly, and still I get the matrix of the tridiagonal form, which is which will be a much simpler from that like the original matrix, like Hamiltonian matrix, if we try to construct out of all the bases. So can Lanchos method be applied there, where we take that capital M to be equal to D, the exact dimension of the Hilbert space? Like still the matrix element will be tridiagonal and sparse.
Actually, you construct first the full matrix of dimension with the exact dimension, and use that full matrix to construct a small Lanchos matrix. You don't construct the Lanchos matrix starting from the operators. You always construct Lanchos matrix starting from the matrix of the full dimension. Okay, so from that you get the tridiagonal matrix, and then you diagonalize.
It's a kind of basis transformation.
Yeah, this is a small matrix.
Right. Basis. Right. Okay, so maybe the thing, I think Professor Ramashesha was talking about this stochastic series expansion, SSC method for treating spin systems, and you talked about Langsdorff's method.
Yes.
If I remember correctly, that SSC method has this problem if the system happens to be a frustrated system, right? So for Langsdorff systems, you don't have such a problem, right? You can deal frustrated systems
Yeah.
also. Okay, good. So this is possibly one of the advantages where people can use exact dimension method.
Yeah, but there are better methods than Lanchos methods.
No, fine. So maybe I again correct me. I heard about this Davidson method. Is it a better method?
Much better method, because it combines Lanchos
Okay.
and the coordinate relaxation methods.
Okay.
Can construct a small matrix representation, which is much better.
Okay, good. So
And that is widely used.
these days, so that's what I've been hearing. Yes. Okay, so if there are no more questions, let's thank the speaker once again. Good. So again, Aston here at 2 o'clock, right? So 2 o'clock. Again.
So we have either, sorry, lunch at the same place.
No, exam is common.
Either we'll let both are at the same place. So please come over there.